Welcome back. We're going to continue our discussion of acids and pKa's in the form of something similar to your test question, but there'll be one extra level on your test question. We'll do that problem right under this one. Before you begin any of these, step 0 is to cross off spectators. And I'm going to make your life simple. I will only use spectators from the first column of the periodic table: lithium, sodium, potassium, rubidium, and cesium. I will limit spectators to those. Their only job in life is to balance an anion. They don't participate in any chemistry for this course, so let's get rid of them so we don't have to think about them anymore. Remember, when you cross off a sodium spectator, you better replace the charge that it's balancing, or else you've created what's called a lie. Carbon's not neutral here. If you got rid of the plus ion, then carbon is just an anion right now. Same for sodium over here. We have N negative. Okay, so step 0 is done. Now we can start the problem. Identifying conjugate acid-base pairs is a simple exercise. If you remember, the only difference between the two partners in a pair is a proton. And please remember, when I say proton, I'm talking about H+, hydrogen cation. So if you're going to do this, then you didn't hear what I just said. You connected things that are different by way more than H+. These are different by only H+. And after you've done that, don't worry about the order A, B, C, D. Look at those two. Which one of those has the extra proton? Yes, the one on the left. It has the extra proton. The one with the extra proton's called an acid. Please give me its pKa. It says in part B, we're supposed to give pKa's for the two acids in this equilibrium. This one's acting like an acid by becoming its conjugate base. And that we've learned, let's see, that's a neutral nitrogen in the form of an amine. We've learned, or will learn very soon, those have a pKa of 40. Jump to part D or E while you're right here. E says pKb, and I actually may not have talked about this, and I think I'm correct. I will pick this up in our third segment today, but right now you just have to believe this fact. This is a looking ahead for us. For a conjugate acid base pair, this only works for a conjugate acid base pair. pKa for the acid plus pKb for its conjugate base equals pKw. Now, some of you know what that means. The negative log of Kw is the negative log of 10 to the negative 14, which is negative 14. You don't have to know any of that. Just remember this fact. pKa for an acid plus pKb for its conjugate base is 14. So if I know the pKa for the acid, then the pKb of the conjugate base is 14 minus 40. That is a very strong base. Why is it a very strong base? Well, I know it's strong because it's got a negative pK. That's not pKb, sorry. That's not the answer to my question. So I've had students do this. They say, oh, I'm supposed to explain why that's a strong base? Because it has a negative pKb, Dr. Whitaker. And I say, you just reworded my question, because negative pKb just means strong base. Now, the answer is it comes from an incredibly weak acid, which means it was really hard to take the H off, which also means when you took it off, this thing wants it back big time. So we've got that going on. And then the other pair, different by only a proton. And yeah, your objection to yellow is noted. Which one of those two has the extra proton because it needs a pKa? Well, this C has an H. The same C does not. The pKa of the acid there, remember, this is an alkene. And on our table and now in our brain, we know that's 45. And from what we just learned, we can calculate pKb. 14 minus 45. And let's see, are we ready? We've done part A. We identified the pairs. We got them connected. We wrote the estimated pKa's under the acids. We circled, oh, we did not circle the equilibrium arrow that is favored. That is the whole point of doing this, to figure out which way this equilibrium goes, right or left, right or left. And this equilibrium will go away from the weaker acid towards, away from the stronger acid. I apologize. 40 is stronger than 45. 40 is 10 to the power of 5 times more reactive than 45. Put another way, this acid is less reactive, which is more stable. If you're less reactive, that means you're more stable. And equilibrium always favors the more stable species. I'm just going to write it this way. Always circle the arrow that points to the bigger pKa. That's great to memorize. It's better to understand. Larger pKa. It is more. When you talk about equilibrium, it's always about stability. It's called thermodynamic equilibrium. And a larger pKa means less acidic. Less acidic means less reactive. Less reactive means more stable. Got all that going on. And down here, what I've done, we're not quite done. It's more stable. We're supposed to calculate pKeq and KEq. We'll do that in purple. And this is where we left off last day. pKeq is always the pKa of the acid on the left side of the equilibrium. In this case, 40. Because that acid is reacting in the correct direction as an acid would, giving up its proton to create its conjugate base is in the correct direction. This acid is written backwards. This one, written backwards. So when you did the K, you had to use the 1 over the Ka for that one, which means you put a negative sign in front of the pKa. But guys, you just need to remember, left minus right without exception. Just please don't memorize anything, and don't invoke certain people like Hess's name. No, stop. This is, you've already taken care of the direction of things by having an acid that's going in the appropriate direction and an acid going in the backwards direction. Left pKa minus right. And KEq, you take 10 to the power of negative 5. which is 10 to the power of 5. We have 100,000 times more products than reactants. Yes, we verified our circle and we put a number on it. So you're going to do all of that work. You're also going to do one step before you do all of that work. So what I did down here was I just erased one of the 4 pieces. And I forgot to change this E to an F. It's not a big deal. Change it to an F. I'm getting a little better at this. It lets me change these. So I'm not going to do parts B, C, D, and E, and F because you did those already, but they were parts A through E. We need a strategy for coming up with what that missing molecule is. And the strategy is not look at the top of the page and copy the molecule down. That's not going to be an option. Here's the strategy. 1. So this is for the new part A. Okay. Ooh, weird. Circle the pair that is already there. Circle. We're not going to circle. Connect. Better word. Connect. The pair that is already there. So, yeah, there was a step 0. We're never going to ignore step 0. That was get rid of, in this case, the sodium spectator. If you don't do that, you're probably going to think that the 2 species with sodium are related to each other, and you'll be 100% wrong. So don't do that. We're going to connect the amine at the beginning with its conjugate partner over here. And then you're going to say, okay, which one's the acid like we did before? And I'm just going to say pKb, C above was 14 minus 40, but we don't need to redo all of our work up there. C40, C above. Speaking and writing don't always go together. Okay. B. If question mark is beside a base, question mark is it better be an acid, right? Acids react with bases, is the conj acid of the partner. What partner are we talking about? Well, it's got to be a partner with the other species. Sorry. Anthropomorphization is a dangerous thing. And flip this around. If question mark is beside an acid, that means it's reacting with an acid. Are you going to say that it's also an acid? No, acids don't react with acids. Then question mark is the conjugate base of the partner. Well, which case do we have here? It's beside a base here. It's not beside an acid, so I need to draw the conjugate acid of the partner. Where's the partner? The partner's right here. Where are you going to park that proton? Take a wild guess. If you put it any place but here, you've created an octet violation. Don't do that. So you're just going to scribble down. In fact, I encourage you to go to stick figures every time you can. Want to put the H on? I mean, you don't have to. There it is. There's your question mark right there. If you want to draw it this way, it's fine. Draw it this way, perfectly fine. This is perfectly acceptable every time unless you're told to draw a Lewis structure, which you're not. So that is, let's see, how much time we got? 48. Let's do our own version of this with a brand new example. Parts A through F again. A through F from Prev page. This time I'll start with a question mark. And our question mark was beside, in the previous example, we want a complementary example, don't we? It was beside a base. So it was an acid. This time I want my question mark to be a base reacting with an acid. So let's do this acid right here. And here we go. So base with an acid, huh? Nice. So there's the whole question. Put our answer below. Any spectators to cross off? Yes. Then we start with our thing. Start with the pair that is already there. Well, clearly this guy's partner's missing, not because of color coding, but because there's no sulfur here at all. The other two species both have sulfur. This acid, where is it on our pKa table? Well, you're going to need to find it. There's a separate section that talks about it. That one is the organic chemist's equivalent of sulfuric acid. It's called para-toluene sulfonic acid. Please learn it. Please learn the breakdown of its name too, even though some of it's a preview for Orgo 2. The para part has to do with the fact there's a benzene with two groups on it. And the para positions are when the groups are as far apart from each other as possible, as opposed to if the sulfur was here, it'd be meta. And if it was here, it would be ortho. You should learn those. It's been known to show up on PCATs and DATs and MCATs. So we have para-toluene sulfonic acid, and it's listed as one of our 7 strong acids. So we have to know our strongest acids have pKa's. Doesn't like me being on the bottom of the screen. -5. So you can calculate the pKb right away for its conjugate partner. 14 minus -5, 19. That means these two need to connect. And this thing's reacting with a base. Therefore, this thing must be an acid. Is that right? Did I mess up? I don't think so. Acids don't react with acids. Base plus, this is the acid. What am I saying? That's the base. This thing's reacting with the base. This is the acid. I need its conjugate base over here. And that's a good question. What is the conjugate base of this? I'm going to copy this molecule if it lets me. And we'll have a little discussion about what to do with what happens when the molecule, oh, there's no H there. A little foreshadowing there. Oh, it shouldn't be blue. Although having a different color is not a bad idea. Let me show you all the pKa's here. There's a double bond I didn't copy over. It has pKa's here and here that are both 45. And I'm going to point to these. No pKa equal 25. Alkyne has no H's attached. Some people see the alkyne and they see the pKa table with a 25 there. Say, it's got to have a pKa of 25. That's only if there's an H attached to the sp carbon. So no. The winner of the pKa wars here. Alcohol, pick a 17 or an 18, either one. So which of these two reacts a lot faster, which means it's the only one that matters? And the answer is the stronger acid always reacts faster. Yes. So it's the only number that means anything. And yeah. Stronger means lower, or pKa means stronger. And so we're going to use pKa 17. Oh, it's over here. And its conjugate partner, pKb. We haven't drawn the conjugate partner yet. You ready for it? Here it is. What's the conjugate base of OH? Don't say just O. You're going to lose a half point if you leave it there. Do you want to lose a half point? Don't lose a half point. There's your question mark right there. And its pKb is, we didn't do it yet. -3. pKa for an acid plus pKb for its conjugate base. And thank you for not interrupting, because I know some of you spotted that. I said pKb and wrote pKa. pKb is 14 minus the conjugate acids, pKa, -3. Strong base. Strong base with a strong acid. This is a dangerous reaction, by the way. Which arrow do you circle? Which one's a more stable acid? -5, which is very unstable, or 17, which is quite stable. This time we're also pointing to the right. We should get a negative pKeq. Want me to prove it? Negative means goes to the right. Positive means stays to the left. You take the acid on the left side of the equation. You subtract the acid on the right side of the equation. Here, I don't want you to think the O is part of a number. There you go, -5. -22. How do we know we circled the right arrow? 10 to the power of +22. Negative is positive. And I believe we got all the parts done here. And that's a good break. Yes, we have a question.
Yes, the potassium atom, where does it go on the left side?
Why did we do step 0? Step 0 was cross off the spectator.
Okay.
And then look back, listen back in the video. It says, we do that so we can ignore it for the rest of the question. The
Okay.
potassium ion will be floating around in this solution, not doing anything all day.
Okay.
But when we list formulas, we need cations for every anion. So that's why they get listed, right?
Mm-hmm.
In the real universe, you have as many cations as you have anions. But for us, we're always going to cross off the spectator, and then we don't have to worry about it. If you needed a place to park it, it would be here, wouldn't it? You put OK there. And I would give you full credit if you wrote OK, O with a K, but you don't need to. Please don't.
Mm-hmm.
Okay?
Thank you.
You're welcome. And we'll see you all on the other side of the break.